sorry, I'm busy.
All right, guys, we left off yesterday talking about the multiplicity and the effect that it has on the graph. We saw that when a 0 repeats an odd number of times and has an odd multiplicity, then that 0, the graph will cross over the x-axis. And the higher that multiplicity is, the more of the flattening out effect it has. All right, we saw zeros with even multiplicity, zeros that repeat an even number of times, then they're just going to touch the x-axis and be tangent to it and bounce right off of it. And the graph will not change sign on either side of that x-intercept, okay? And then we have the end behavior. We've already talked about it a number of times, but let's put it in its fancy language now. The end behavior of a polynomial, it's going to depend on that leading power function, because that's what happens when x is a large value at either end of the graph. It really only comes down to who was that leading power function. So we said if the polynomial has an odd degree, degree 1, degree 3, degree 5, and so on, then the end behavior will be what? Different or the same? Different. Thank you for one person. Different, opposite. So I always think of that as one end of the graph has to be pointing up and one end of the graph has to be pointing down. But then it's kind of like, well, which end will be up and which end will be down? Well, guys, think about y equals mx plus b, right? Think about a straight line. M is our slope, but he's also the leading term and your leading coefficient. When the slope was a positive number, which way did the line slant? To the right or to the left? To the right. So when that leading coefficient is positive, your graph will end up on the right side, the positive side of the graph, and down on the left side, the negative side of the graph. So if A, and A being that leading coefficient, if the leading coefficient is positive, then the graph will always be up on the right side. And I always think of the right side as the positive side of the graph, and it'll be down on the left. Okay? So then we can say, if that's true, when the leading coefficient is positive and it's up on the right and down on the left, then we can say the end behavior is this. As x goes to positive infinity, as x gets bigger and bigger and bigger, what is that y coordinate going to go to? Infinity. F of x will go to infinity. And then as x goes to negative infinity and gets really, really, really small and really negative, then what will f of x go to on that end of the graph? Negative infinity. And guys, that is that different end behavior. One y value goes to infinity, the other y value goes to negative infinity. All right, and then let's say that straight line had a negative slope. So that leading coefficient was negative. Now which way did the line slant? To the left. So now when A, that leading coefficient is a negative number, now it'll be up on the left side and it'll be down on the right side. And these are rules that we're going to be able to use to help draw really quick sketches. All right, so if that's true, if it's up on the left and down on the right, then in this case, the end behavior says, as x goes to infinity and gets really, really big, what is f of x heading to on this end of the graph? Not infinity, but negative infinity. All right, and then as x goes to negative infinity and gets really, really small and negative, now what is that f of x heading towards? Infinity. And again, there's that different end behavior. One y value is going to negative infinity, and the other one is going to positive infinity. They have different end behavior on an odd degree polynomial graph. All right, perfect. Well, then even degree polynomials. We said if the degree was even, then what did the end behavior have to be? It's not different, it's the same. So they are either both ends are up or both ends are down, but they have to be pointing in the same direction. Well, guys, think of a very easy even degree polynomial. Think of y equals ax squared, right? When a was a positive number, we know the parabola opened up. When A was a negative number, we know the parabola opened down. So when A, your leading coefficient, is a positive number, what will both ends do? They'll both point up. Okay, so then we can say the end behavior is this. As x goes to infinity, and gets really, really big, then f of x will go towards, what's this y value going towards? Infinity. And then as x goes to negative infinity and gets really, really small and negative, what is f of x on this end of the graph still going towards? Infinity. And guys, there's that same end behavior. Both ends of the graph are going to go towards positive infinity. All right, and then last rule, if the leading coefficient was negative, then we know the graph has ends that both point down. All right, so as x goes to infinity, f of x is going to negative infinity. Beautiful, thank you. And then last, as f of x goes to negative infinity on this side of the graph, who's f of x still going towards? Negative infinity. And there's that same end behavior. It matches. All right, perfect. So sometimes on the homework, they make you fill that in as x goes to infinity, and it's a drop down sometimes, okay? All right, perfect. Let's try it. Let's try to use all these rules to come up with a quick sketch. All right, so they've given you basically a laundry list of things that you have to find to analyze the graph of a polynomial, which is fine. Some of them are really, really quick and easy steps. All right, so we have this polynomial function right here. In part A, it says list each real zero and its multiplicity. So guys, let's find the zeros. Let's set it equal to 0, and let's solve. Luckily, it's already in factored form, so I don't have to worry about taking this higher degree polynomial and breaking it down and factoring it. I do have this degree of 3. It's a habit of mine. I like to expand anything that has a power on it. So this is a negative x. This is x plus 2, one time. And I really have 3 of those factors. You do not have to do this. It's just something I like to see. All right, since it's already factored, let's set each factor equal to 0 and solve. So if I set negative x equal to 0 and solve, divide by negative 1, we get x equals 0. So that is a real number that is going to be an x-intercept on the graph. What is his multiplicity? How many times did he repeat? 1. Okay. Then we set this factor equal to 0, we get negative 2. How many times did this one repeat? So multiplicity is 1. This one we're going to set equal to 0 3 times, and you're going to get x equals 3, 3, and 3. So guys, it's really creating one x-intercept at an x value of 3, but it did appear and repeat 3 times. So what's the multiplicity here? 3. Okay, so we found our zeros. Those are all real numbers. They're all going to be an x-intercept. Part B says, determine whether the graph crosses or touches the x-axis at each x-intercept. So remember, that depends on whether it was an even multiplicity or an odd multiplicity. So guys, if this x-intercept had a multiplicity of 1, that's odd. Did we say odd multiplicity is going to cross or just touch? Cross. That's going to be a cross. And since it only repeated once, guys, it's a normal cross. It's just going to pass right through. There's no flattening out. It's just a crossover. All right, this x-intercept had a multiplicity of 1. So is that going to be a cross or a touch when the graph gets there? Cross, because it's an odd multiplicity. And then again on this one, now it repeated 3 times, multiplicity 3, which is still an odd multiplicity. So will the graph cross or just touch? Still cross, but it definitely is starting to repeat more than just one time. So it probably has a little bit of a flattening out effect as it crosses over. The important part is that it crosses. So if you don't actually end up drawing the flattening, it doesn't really matter. All right, then it says, Determine the maximum number of turning points. Well, guys, in order to do that, in order to say how many max times it could turn, you need to know what the degree is because there's a relationship there. So let's skip to part D. We'll have to come back to part C. Part D says, determine the end behavior, bless you. That is, find the power function that the graph of f resembles for large values of absolute x, positive or negative x values. So guys, in order to do that, we need that leading power function. I need to know who would that leading term have been. Well, guys, technically, in order to do that, you need your polynomial in standard form, all multiplied out so you can see each individual term. But in reality, if you think about FOILing, the leading term always comes from just multiplying your front of your factors together. So all we have to do to figure out who that leading power function is, guys, just distribute the fronts. So what's negative x times x? Negative x squared times another x would be negative x to the negative x to the, and then negative x to the fifth. I swear to you, if you took the time and multiplied that all out and wrote it in standard form, the leading term would have been negative x to the fifth. So we don't need to do the rest. That would have been your leading term, your leading power function that we know the end of the graph is going to dictate. All right, so if that's true, what degree is this polynomial? It's degree 5. So if it's a degree 5 polynomial, what's the maximum number of x-intercepts it was allowed to have? You're thinking turning points. At most 5, right? The degree tells you the number of zeros, the number of x-intercepts. If it's degree 5, that should match your x-intercepts. And guys, we got 1, 2, 3, 4, 5 zeros, 5 x-intercepts. Now, the max turning points, though. If it's degree 5, what's your max TP? What is it? Not 3, 4. 1 less than the degree. Okay? Now they want the end behavior. Well, guys, the end behavior is definitely based off of the degree, but we also saw it's based off of that leading coefficient, whether it was a positive value or a negative value. So now we can say the leading coefficient is who? Negative 1. These are all things you're going to have to use to predict that end behavior. So guys, if it's an odd degree, what does the end behavior have to be? Same or different? So we know it's 1 up and 1 down. Now the question is, who's up and who's down? If the leading coefficient is negative, think of that straight line that had a negative slope. Which end of the graph was up? The right or the left? So we know it's going to be up on the left and down on the right. Now I'm going to wait until we put the graph together to write the fancy talk. Okay. Then it says, sketch the graph of f using your zeros, their multiplicity, and the end behavior. So guys, give yourself a coordinate plane. And right now, let's only label our x-axis. Okay, so we had an x-intercept at 0. Put an x-intercept at 0. We had an x-intercept at -2. Put an x-intercept at -2, and we had an x-intercept at 3. Put an x-intercept there. Those are the only 3 spots where your graph is allowed to touch or cross over the x-axis. Nowhere else was there an x-intercept. So your graph should not touch or go near the x-axis anywhere else. All right, normally they do ask you to find the y-intercept. I don't know if it's here, but let's do it because it's another point that you know your graph has to pass through. So guys, if you want the y-intercept, who does x have to be? 0. So let's just plug in 0 and let's find a y-intercept. So I'm going to plug it into the original. So guys, -1 times 0 plus 2 times 0 minus 3 to the third. The minute you make that first x 0, what's 0 times all that other stuff going to be? 0. So now you know the y-intercept is 0, 0, and we already have it plotted. The rule is, guys, if you have an x-intercept at x equals 0, then he's obviously your y-intercept too. Okay, we're ready to do this. Let's let the graph fill itself in based off what we know. We know it's degree 5, so no, the end behavior is different. We know the leading coefficient is negative, so we know it's up on the left side and down on the right. So guys, to the left of your last x-intercept, make sure your graph ends up. We know it's going to. Your graph has to be above the x-axis to the left of the last x-intercept. We know it's down on the right. So to the right of your last x-intercept, make sure your graph ends down below the x-axis. Now we said every single x-intercept had odd multiplicity. So the graph is going to cross over every single time. All right, the graph's gonna fill itself in, watch. If I know my graph has to end up here, then start your graph there and head towards your first x-intercept. Oh, you know what? Okay, yeah, I'm good. That was x-intercept -2. Multiplicity 1, that's a normal crossover. Now here's the beauty of these sketches. I really don't care how far down it went. All I know is that these x values made positive y's come out, and now these x values are gonna make negative. That's all we care. So guys, think about it. The graph is going down. What does the graph eventually have to do somewhere to get to the next x-intercept? It's gonna turn. So make it turn. I don't care. This is where we're all gonna be different sketches. So make the graph turn in a nice rounded fashion. Now it gets to this x-intercept. X-intercept at 0 had multiplicity 1. That's normal, cross right over. All right, so now your graph is going up. Now it's above the x-axis. Eventually though, what do you know your graph has to do to get to the next x-intercept? It's gonna have to turn and start going down somewhere. So make it turn. All right, now, this multiplicity had a multiplicity of 3. So we know it's crossing, we know it's odd. Technically though, what should the graph kind of start to do as it approaches this x-intercept because of its higher repeating fashion? It should start to flatten a little bit. The graph kind of slows down as it crosses over here. But like I said, at the end of the day, I don't really care if you show this because the important part is that you make it cross. But to be a little technical, because it's starting to repeat, as it approaches, it flattens out a little bit and then crosses over. So there's this little bit, I used to call it a sit. I used to feel like it made like a chair, like the graph just kind of sat and paused for a second. But that's either way. Like I said, if you crossed right over, I'd still give you 100% credit. And now I have no other x-intercepts to head towards, and I know my graph should end down. So you're done. So last year, if you remember, when you were doing this in Algebra 2, they would make you find your x-intercepts, and then they would make you plug in x's over here, see what number came out, get a legit point. They would make you plug numbers in here in, get a legit y value out. They would make you plug x values in here, get a legit y value out. And they would make you plug x values over here in to get a legit y value out. We don't really need any legit y's anymore. All we care about is that on this interval of x, y is positive. On this interval of x, y is negative. On this interval of x, y is positive, and on this interval of x, y is negative. That's all we care about in pre-calc. Where is the f of x positive or negative? I don't actually care what physical number it is. And the graph literally fills itself in based off of your rules. All right, so now that we have the sketch, let's just fill in the fancy talk, the end behavior. So we can officially say the end behavior as x went to infinity, as x got bigger, who did f of x go to? Negative infinity, beautiful. And then as x goes to negative infinity, on this end of the graph, who did f of x go to? Infinity. And there's that different end behavior. Someone's going to infinity, and the other one is going to negative infinity. Do you guys kind of remember doing these graphs last year? A little bit, yeah? Okay. Like I said, normally they make you get a much more exact graph. And if that's comfortable for you, guys, have at it. You can plug as many x's as you want in if you're confused as to where the graph should be. I'm just trying to give you time-saving strategies. All right, let's try one more, and that's probably all we're going to be able to get in today. Just make sure I answered all the questions. We should be good. All right, here we go. So let's go through the motions. List all of the zeros and their multiplicity. So guys, let's set this equal to 0 and let's solve. I'm going to expand it if it needs to. All right, let's set our factors equal to 0. Let's start getting our x-intercepts. So I set 2 equal to 0 because he is a factor, but I don't get a result from him. I don't get an x-intercept. I'm going to get -3. and I'm going to get -3. So what multiplicity does that one have? 2. Okay, I'm going to get x equals 1 time. So what multiplicity is that? 1. And then I'm going to get x equals 4. And that's multiplicity 1. Beautiful. So guys, if I'm you, this is what I would do. Let's start graphing it as we get it. Let's throw our x-intercepts right up there on the graph. And again, those are the only spots where your graph is allowed to come anywhere near the x-axis. Guys, every year I have a student who does stuff like this. They cross over, and then I'm like, I'm going to come back. Oh, no, I got to hit this one. Why are you crossing there if you didn't have a dot? Don't do that. If there's no dot, don't you dare cross. Go ahead, Andreas.
Isn't the period short?
It should be 25 minutes long.
Okay, because, so I'm like,
Yeah, it's definitely shortened. I thought the announcers were about to cut me off too. But yeah, it's only 25 minutes. I'm just trying to get as much as I can done before they cut me off. All right? All right, so we have our zeros, our x-intercepts. Then it said determine whether the graph crosses or touches. Well, guys, if this has multiplicity 2, which is even, does it cross or touch? Touch, which is a touch of bounce. All right, multiplicity 1 will just be across, just like normal, no flattening. And then multiplicity 1, that's another cross. Odds cross, evens don't. Okay? All right. Then they want the max number of turning points, which again, you need your degree. So let's go get that leading power function that the end behavior will be dictated by. So guys, distribute your fronts. 2 times x times x times x times x is going to be 2x to the beautiful. That is the leading power function that the entire end behavior of the graph will be based off of. So what degree is this polynomial? 4, which means it can have at most how many x-intercepts or zeros? Oh, I keep messing you guys up. The x-intercepts or zeros equal the degree, so they can have at most 4. But then the max turning points will be 3. At most, the degree minus 1. Okay, and then what else? Well, let's get the leading coefficient right now because we know he's going to have to do with who's up and who's down. The leading coefficient here is who? 2, which really, I don't care that it's 2, I care that it's positive. All right, well, guys, if it's degree 4, what does your end behavior have to be? Both up, both down. If the leading coefficient is positive, it's both up. Okay? All right, let's get the y-intercept real quick. It's just another point that our graph can go through. So guys, plug in a 0. 2 times 0 plus 3 squared times 0 minus 1 times 0 minus 4. That's 2 times 9 times negative 1 times negative 4. That's positive 72.
The pledge to the flag. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Please be seated.
All right, I'm going to finish it. So we have our y-intercept, 0 went in, positive 72 came out.
The class of 2023 will be having a big
All right, let's do it, guys. We said that they both have to be up. So to the right of your last x-intercept, we know the graph has to end up there, above the x-axis.
Anyone interested in
To the left of your last x-intercept, we know the graph has to end up above the x-axis. I give myself targets, so I know where I'm going.
But are interested in playing.
All right, watch the graph fill itself in. Just watch out for the touch. And that happened at -3. So sometimes I'll mark it to remind myself he's special. All right, so we know it ends up here. Let's head towards the first x-intercept, but what's the graph going to do? Touch. So literally touch it, but then bounce right back up. For the love of God, don't cross over. It doesn't come out the other side. So now, from here to there, look at what your graph has to do. It's got to go up, obviously, hit your y-intercept because it's in between these x values. And then for all you know, guys, maybe it keeps going up a little bit more. But eventually, and rather quickly, what's the graph gonna have to do to get to this x-intercept? It's gonna have to turn and come down. Now, don't go past it, you have to stay here. Now when it gets there, it's a multiplicity 1, so what does the graph do? Cross. What's your graph gonna have to do to get to your next x-intercept? It's gonna have to turn. When he gets there, what's it gonna do if he's got multiplicity 1? Cross. And there's no other x-intercepts to turn and head towards, so you stay up. So obviously they're not the prettiest picture, but guys, that's all we care about. We know these x's make positive y's. These x's also make positive y's. These x's make negative y's, and these x's make positive y's. It's just telling you where f of x is above or below the x-intercept and for which x values. All right. Are you guys okay? Yes? All right, so that's just a quick way to get your graph of your polynomial. And then I'm going to fill in the end behavior up here if you want to write it down.
Jordan Mann, Anthony Martini, Sydney Slimore, Jamie Gertine, Jean-Claude Yandau, Evan Liu, Madeline Grabowskis, Ava Orlando, Natalie Barr, Jillian Briggs, Courtney McCann and Antonio, Raymondo,
So please just keep working on that homework that I've already assigned.
Joseph Flatley.